Good morning. Today we will continue our last day's discussion, that is oscillator. So, if we recap, last day we have covered linear oscillator, right. We have covered the Barkhausen criteria. If we see a negative feedback structure, this in feedback we have studied the advantage of negative feedback, right, and in oscillator we will be studying the advantage of positive feedback. So, if we have a positive feedback, then our closed loop function is a by 1 minus a beta, and from this we have derived the oscillator criteria, that is if the loop gain is 1 at a particular frequency omega 0, where the phase is 0 degree or 360 degree, then there is a chance that this oscillation can build up. Now, we have two type of oscillator, one is linear and one is non-linear. So, we have covered the linear portion. In this linear portion, we have one frequency dependent circuit, that is RC component or LC component, right. So, which can select our frequency, and we have another gain element, right. So, another is, so one component must be some frequency selective component and another component is our normal gain element. Now, as you said that the condition is that initially we should have higher loop gain. Okay. When the oscillation is building up, we should have a this is slightly greater than 1, and as oscillation starts, then we will move to 1. So, we have some variable gain. Okay. So, this limiter circuit, this actually limits this from little bit higher gain to L is equal to loop gain is equal to 1. So, that is the concept of limiter circuit, that we can the same circuit we can superimpose over here. And this Wien bridge oscillator, this component you see, one R and C is in series and one R and C is in parallel. So, this structure we can make it op-amp based active oscillator, or we can also make it discrete component based. We can use this same R and C component and use with a MOSFET or BJT to design a oscillator. Okay. In your lab you are doing which kind of oscillator, this op-amp based or MOSFET based? Op-amp based. Okay. So, how to decide that what is the, so what is the oscillation frequency omega 0? What we will do? First we will try to derive this node voltage. Okay. How to derive this node voltage? So, it will be something like that, right. So, if I have a V 0, so this is my Z series and this is my, so this is my Z series and this is my Z parallel, right. So, this structure, this one and this one, they becomes a potential divided like structure, right. So, I can find this feedback element, okay, that is ZP by ZP plus ZS, and these two are my the closed loop gain of the op-amp, and if we multiply them we will get the L. Okay. From this, if we restructure them, we will get a by 1 plus JB kind of structure, and from that we can calculate the frequency where we have a chance that phase is 0. Okay. So, similarly from an RC circuit we can see that for a single RC circuit it phase goes from 0 degree to minus 90 degree, and as minus 90 degree it is frequency is very high. So, in between somewhere we can consider that one RC circuit can give us a phase of 60 degree. So, we have considered that 3 are giving roughly say 180 degree. Okay. So, now to satisfy the Barkhausen criteria I need another 180 degree to get a total of 360 degree. So, this is the concept. So, one RC circuit is giving me a phase delay and I am combining 3 RC circuit to achieve a phase delay of 180 degree, right, and we are adding another 180 degree. So, if it is inverting type, that is providing out of phase 180 degree. So, if we can combine this kind of circuit, we can design one phase shift RC phase shift oscillator. These are known as RC phase shift oscillator. Okay. So, this portion is one single RC element, 3 RC element, and this is connected in negative feedback. This quadrature oscillator, this is one integrator, is connected with other, this is also one Miller integrator type circuit. Okay. Amplifier 2 is a non-inverting, connected as a non-inverting integrator. Both are, this is Miller integrator, this is not, this is also another kind of non-inverting integrator. So, if these two are connected in back to back, then we can have this V01 and V02, they will be having 90 degree phase difference. That is why this name quadrature oscillator. In some applications we may need multiple phase shift. Okay. So, this is one of the circuit which will give you 90 degree phase shift between the V01 and V02. Now, another type of filter design is that you will be having a square wave generator and a band pass filter. Okay. So, I will generate a square pulse and will put it in a band pass filter. So, band pass filter what it will do? It will block certain frequencies, right, and it will smooth the square wave to a sine wave. So, same way we can come to LC oscillator. Now, in LC oscillator you will be coming across the concept of tank circuit, right. So, when you have a inductive part and a capacitive part, and if you connect them, so there will be a oscillation between the energy will, the capacitive portion will supply the energy to the inductive portion, and when it will reach the full, then this capacitor portion will be off and this inductor will again dissipate back to the capacitive portion. So, this will keep on oscillating at a particular frequency, that is omega 0. Okay. That is called the resonant frequency. It will oscillate at a frequency that is omega 0, and there is another term that is Q factor, that is omega 0 L by R. Okay. Or you can tell that this Q factor is the definition of the inductive portion divided by the resistive part, right. So, resistive part is where all your loss is happening, right. So, this Q is also a definition of your amplitude. Okay. So, this is a response of a band pass filter, right. So, this is your center frequency and this is your bandwidth. So, if you have a high Q, you will be finding a selectivity. Selectivity means your F by del F, that will be high, right. So, this is your Q factor, that means it will be sharp. Suppose you have a radio, you want to tune a particular channel. So, what you are doing, you are actually changing this L and C components and trying to modify this, catch this FC. So, when this FC is matched, you will get that particular channel, and all other channels, suppose here is another channel, that will be not selected, clear. So, this selectivity, this is quite high. So, this amplitude, suppose if your resistive portion is high, then your amplitude will go down, right. So, that is the, we generally say as a quality factor, okay, Q. So, we can have this LC oscillator also. So, we will be having some capacitive portion and we will be having some inductive portion. Okay. Now, there are two type of variation, one is you see the capacitor is connected like a divider and here the inductor are connected like a divider, and this R is generally the passive component of this capacitance and the inductance. Each inductance will have some lossy part, right, that is our resistance. Okay. So, two type of variation where this emitter is connected to the middle of this capacitor connection and here this emitter is connected to the middle of this inductive connections. So, they are named as Colpit and Hartley oscillator, and in Hartley oscillator our omega 0 is equal to 1 by square root of summation of L into C. I have 2 L, so summation of L into C, and in Colpit oscillator I have 2 C. So, they are in series, that means their connection it will be C1 C2 by C1 plus C2. So, it is omega 0 L into 1 by square root of L into C equivalent. C equivalent is C1 C2 by C1 plus C2. Okay. So, this is how we can calculate the oscillation frequency. We will not get into details of oscillator circuit, there will be several oscillator circuit, we will be just considering the basic concept, okay, concept and working principle. So, this frequency of oscillation will be determined by the resonance frequency of the parallel tuned circuit, also known as the tank circuit, because it behaves like a reservoir for energy storage. So, this is the complete circuit of the Colpit oscillator. So, can you tell me which kind of amplifier this is? Common emitter. So, this portion is your suppose Z and this is your emitter degeneration resistance that you can short bypass. Okay. So, this structure you have studied in details. So, what will be the gain of this circuit? Suppose this RE is not there, it will be minus GM into RZ, GM into Z, and if this RE is considered, this is GM into Z by 1 plus GM into RE. Okay. So, you see such a big circuit, but if you simplify this, if you consider that this is a single block, right, and this portion, can you tell me why this is used? Potential divider to generate the base emitter potential. This is for biasing, DC biasing. You need to bias this at which region? Active region. Okay. So, you see all the structure you know. Now, next is some concept of multi vibrators. Now, in multi vibrator we can have two stable state that means if it is in 0, it can stay in 0. Now, I need some trigger to go to 1. So, this state is stable, and if it goes to 1, then again it is stable. I need another trigger to go to 0. Okay. So, stable state means by default it is it can stay in that state. I need some trigger to move to the other state, trigger will force it. So, this is known as the bistable. If I have a single stable state, that is monostable. Okay. One state is by default it will go to that stable state, and if none of the state is stable, that is astable. Okay. Now, we have a circuit that is called comparator, or this is hysteresis loop. Okay. This circuit we are having, you see, when this input goes above VTH threshold voltage, okay, this input is increasing this way, Vi is increasing, right. So, the moment Vi is above a certain voltage, your input is connected to which terminal? Inverted terminal. So, if Vi is above this V plus, this output will be minus. So, this Vi plus, this V plus is my VTH threshold voltage. If Vi is above this V plus, this will go to minus VCC. Okay. So, the moment it goes to minus, this component will also go to, suppose this previously this V0 was plus. So, this V plus was also in plus, it will be less, how much? R1 by R1 plus R2 into VCC, right. So, the moment input crosses this value, it goes to minus. So, this voltage will now becomes V minus. So, that will become V threshold high, and now it will become V threshold low. Getting my point? Previously it was output was positive. So, this threshold voltage is also positive, you see it is on the right hand side. The moment this goes to negative, this V plus, that will now become V minus, right. One value is V1 R1 by R1 plus R2 into VCC. Another value is R1 by R1 plus R2 into minus VCC. So, this is VTL, threshold voltage low. So, now this voltage need to drop below this to go to the high. Getting my point? So, suppose you have a single VTC. So, if it is less than that, it is positive, if it is higher than that, it is negative, inverting connections. Now, rather than a single point, this can vary. So, now I have two comparison point, is not it? The path are different, you see. So, this kind of, if I have a two path, so if it is going this way, then I am following this path. But if it is going the other way, if it is going from low to high, I am going V threshold low. If it is less than V threshold low, then only it change states. But if I am going from high to low, this is following another threshold, that is V threshold high. So, what I am having now? Two different path, right? One path for high to low and another path for low to high. So, as if it is having some memory, right? It is memorizing what was my last state and choosing its crossing points. So, this one was having a single. Now, I have a, this is like what, hysteresis, right. This is known as a hysteresis plot, right. So, it will show a, this is our Smith trigger, this has a typical name, that is called Smith trigger. When I am going from low state to high state, my comparison point is something else, and when I am going from the other state, my comparison point is something else. So, you can understand that this is also a multi vibrator circuit, this Smith trigger is also a multi vibrator circuit. Okay. Now, this kind of bistable circuit, we can use, this Smith trigger can be used as an comparator, right, and this also can be used as a function generator for design of this nonlinear oscillator. Okay. So, how we can do that? So, there is another advantage of this hysteresis. Suppose our signal is very noisy. Okay. I have a digital circuit. Each time it is crossing, I will have a false transition, right. Right. So, each time it is crossing say 0, suppose this is an inverter, okay, and each time it is crossing 0, it is falsely treated as 1 and I am getting a 0 here, but this is not actual 1, right, this is some noise actually. Okay. So, what I can do, if I can increase my limit, that up to this you do not consider, if it is crossing this, then only you consider it as a 1, right. So, what I am doing now, if it is zigzagging, still I will not get a, I will still it will consider it as a 0. The moment it will cause this V dash, then only I will be considered this as a input 1. So, now apart from this I have increased my noise margin, is not it. Previously each time it was crossing 0, it was falsely treated as a signal, and from 1 it was coming to 0. And in the one side also I will have having a margin. So, this you can think of V threshold low, and this you can think of V threshold high, right. So, now unless it is going over V threshold high, I will be still consider this as 0 input. So, this hysteresis kind of circuit, this Smith trigger circuit, I can use it this Smith trigger I can use as an digital logic. So, that now I have a, even this is bouncing, still it will not, the output will not be reflected, and even if it is bouncing, still it will not be. So, if I consider this is an inverter, the inverter output will be clean. Otherwise, for each of these I would have something like this. Okay. So, this is clean, this output is clean because I have a margin now. Okay. So, this is another advantage of the Smith trigger. Now, we can use this multi vibrator to generate some square and triangular waveform, okay, and we can also use some filters to generate the oscillation. So, we will be having some this Smith trigger, and we will be having one RC component. So, I will be having two threshold value. If this output voltage is plus, I will be having one positive component, and if this output voltage is minus, then I will be having another negative component. So, two comparison point I am getting, one is threshold voltage high, another is threshold voltage low, and it will keep on doing that. So, here you see it is none of the state is stable, the moment it reaches the other threshold it switches. So, this is one astable multivibrator. I have used one RC component. So, what will happen? This RC will keep on charging, right. The moment it will reach this threshold high, the Smith trigger will, what is happening here? The moment this Vi is above this, it will go to minus, and the moment Vi, when it goes to minus, the moment it is below that, it will again go to change the state, right. So, it will keep on oscillating, right. This is behaving like a comparator, right. So, what is happening, if your Vd is positive and one is Vd is negative, right, and your this is inverting. So, it will go to minus Vcc, it will go to plus Vcc, right. So, same thing will happen here, RC component is building up, RC component will increasing, right. So, the moment it will try to go above that, it will change its state, and the moment it goes to the other side, my threshold voltage is also. So, what will happen to this RC component? It will now start to fall. The moment it will fall from this threshold voltage low, it will again change its states. So, it will keep on oscillating between two states. Okay. So, this is an astable, complete on total it is an astable multivibrators. So, without the RC component it was an bistable, with the RC component it becomes an astable. So, the movement of V we are doing using this R and C component, V is changing like this and this, okay. And this is our output, output will be some oscillatory square wave. Clear? This operation is clear or you have any doubt? Understood? So, what is happening? This node voltage, if we consider that as Va, this is charging up, and the moment it is getting above this voltage, it is changing its states, then again it is falling. The moment it is changing its state from this voltage, falling below this, this will again go up, right. One is Vp, one is Vn, isn't it? If it is positive, this Vp is this value. If this output voltage is negative, this is this value. So, I am getting two comparison point rather than a single transition point. Now, I am having a two transition point. Clear? So, you think it little bit about it, it will be clear to you. Next is triangular waveform generator. So, here this node, you think about this RC node, you see this is like a exponential, right, and if we approximate it, we can get a triangular wave. This is an exponential, right, and if we take a portion of this, that can behave like a triangular wave, right. So, the same principle, same circuit I can use to get triangular waveform generator and a square waveform generator, right. From this I will get the square waveform, and from this node I will get the this node in this circuit. This node is giving me the triangular waveform and this node is giving me the square waveform. Output of the op amp is giving me the square waveform. So, same philosophy I can get one square wave, one triangular wave. Next is 555 timer. Have you heard of this circuit? Are you doing it in lab? So, in this IC how many pins you are having? 8 pins, right. So, this 5 timers, it is having 8 pin. So, can you tell me why this name 5 timer? 3 5K register, right. Internally I am having 3 5K register. Okay. And what is the purpose of using this circuit? What is the purpose? This is generating some pulse. Okay. Basically, what we read, this wave shape that can generate those wave shape, triangular waveform, square waveform. Okay. And you understand this name timer. So, mainly time means we generally think of clock pulse. So, this square wave is used as a clock pulse. This is our, this will be our T, right, to time a circuit, right. So, that is why it is, and it is quite cheap and quite popular. So, you know little bit about this, right. So, this circuit, this IC connections, we can use all these multivibrators, different states we can design by this circuit, by changing the internal connections, how the way they will be connected. If we change those, we can design some monostable or bistable or astable multivibrator. So, what we will do? We will take some RC element, right. The working principle remains same. What is the working principle? That one RC component is building up. So, this is our variable voltage, and we will be having through two different threshold, one is upper threshold, another is lower threshold. So, the moment it will go and touch those threshold, it may shift, right, and depending on our type of stability, one state may be stable, that will by easily it will go to that state. Suppose I have monostable. So, suppose 0 state it is stable. So, whenever it reaches 1, it will by default it will go to 0, but from 0 to 1 I need to give a trigger. So, this trigger will somehow change this connection and we will force it to go to the 1 state. The moment it will reach 1 state, I am talking about monostable. Okay. So, we can have such a variation, this circuit connections we will modify such a way that we can change it, right. So, you can see there is another element, I have two comparator. You know the functionality of comparator, the input voltage, if it is above the comparison voltage, it will change its state, plus or minus, that will see the internal connections, right. So, comparator you all know. You know RS flip flop or SR flip flop, is it covered? Covered digital electronics, second semester. Okay. So, let me just little bit, let me tell you about the SR flip flop. This is known as SR flip flop or RS flip flop. S stands for set. What is the meaning of set? Output will be set to 1. R stands for reset. Reset you understand? Reset to 0. So, I have two state, set and reset, and suppose this present state is n plus 1. I have a clock, right. What is the meaning of clock? Suppose this was my 0th state, this is my 1st state, this is my 2, right. Each, this is one time period, na. Suppose this is T0, say this is T1, say this is T2. So, suppose T2 is your present moment, you are at T2. So, present moment I am telling it n plus 1. I can tell anything, right, this is naming just. So, previous, if T2 is your present state, T1 was your previous state. So, if this is n plus 1, this should be Qn, clear. output I have S, I have R, I have Q n plus 1. So, output is Q n plus 1. I will be another Q bar, right, Q and Q bar complementary. So, I will be another. So, if this is 1, this should be 0, if this is 0, this should be, this is complementary. Okay. So, I am not thinking about that. If I get this value I will also get. So, that is sufficient. So, these two are my input and this is my output. So, now we will be this truth table, how many combination I can have S and R values? 4 combination. One is 0 0, another is 0 1, another is 1 0, another is 1 1. Now, two things I know, if set is 0, output will be set and reset. If set is 1, output will be set to 1. If reset is 1, output will be reset to 0. These two I know by the name, set and reset, na? Set, reset. Reset means output is, this is reset, output is 0. This is set, output is set to 1. These two I know. Clear? So, when this is 1 and this is 0, output will be 1. And if this is 0 and this is 1, this is 0. These are defined. Now, this 0 0 means I will, whatever the last voltage, I will hold that. So, it will be Q n, and this 1 and 1, this is undefined. This state is called prohibited. For SR flip flop, this is not defined. Let us just once again tell this. Please pay attention. This you will be knowing this. Huh? Suppose my S is 1, R is 0. This is my number 1 state. Set is 1, reset is 0, output is 1. Now, I am changing it to 0. This is my, that was my 1 state, that is my 2 state. Previous state value was what? 1. I am making it 0 0. What I told, if it is 0 0, it will hold the last state value. What was my last state value? So, it will hold it 1. Clear? Suppose now it goes to 0 1, this 0 is changed to 1. Reset is set to 1, so output will be 0. From this, suppose I am again going to 0 0. What will be the output? 0. Last state is 0, it will hold that last state. So, getting the difference, in this 0 0 state it was 1. Why? Its previous value was 1. In this 0 0 state it is 0. Why? Because its previous value was 0. So, it will look for the last state. So, you can think of it is having some kind of memory. It can remember its last state, and its 0 0 condition it will hold that last state. Clear? And why 1 1 is prohibited for this? Basically, in 1 1 what problem happens, this Q and Q bar, their value that should be complementary, right, but for this 1 1 composition their value remains same, but that cannot be possible. That is why we said 1 1 is prohibited in SR flip flop. If this is 0, this should be 1, right, but when you will be doing the circuit, you will be knowing that for this case both the values are coming same, but by default it is against, right, Q and Q bar is complementary. That is why we say this is prohibited. In other kind of filter, JK flip flop, this is okay. Okay, so I am not going into that. So, this is one kind of flip flop. What is the name of the flip flop? State is, you see, flipping, right. each clock it is changing its state. Okay. So, that is the working principle. So, if you know by that, that will be sufficient. So, let us just discuss this operation. This is our VCC and this is behaving like a potential divider, right. So, this voltage is higher than this voltage and this voltage is higher than this 0 voltage, right. So, if I have a connection like this, I will get 3 comparison point, right, 1 comparison point, 2 comparison point, 2 point I am getting. These are known as the threshold voltage. Okay. So, this voltage is when it is above VTH, this comparator will go to 1 and suppose this trigger voltage is above this VTL, this will be 0. These connections are like that. Okay. So, what you get, R is equal to 1, S is equal to 0, output Q will be 0. If Q is 0, Q bar will be 1. If Q bar is 1, this BJT will be turned on. If this is turned on, this discharge will be connected to ground, right. You can think of this is on, so this is virtually short. Okay. So, this is the operation. So, let us see now. One RC component is connected, right. So, this VC will keep on building, right. The moment this VC will go above this, suppose your V0 is high, V0 was initially high and trigger voltage was like this. Now, VC is building up, right. This VC is going to, this is connected to VCC. So, this capacitor voltage will be charging up. The moment it is going above VTH, what will happen? This R will be 1, right, and this trigger at this moment is connected to 0, right. So, this is 0, this VTL is 1. So, this is also at this moment you see this trigger is going to 1, this trigger goes to 1. So, this goes to 0. So, R is 1, S is 0. So, this goes to 0, this goes to 1. The moment this goes to 1, this connection will be sorted to ground. So, this connection is sorted to this capacitor node. Suddenly this capacitor will go to 0, suddenly this capacitor will be discharged. So, this capacitor was building up. The moment this connection is 1 and 0, this goes to, from 1 it goes to 0, this Q becomes 0 na. So, 1 it goes to 0 and this capacitor is suddenly connected to ground or discharge. So, it falls. The moment it falls, this will go to 0, clear. 0 and 0 it will remember its last states, it is staying in 0. You write the step by step. Okay. The VC is building up, step 1, VC is going up, VC is above this. Okay. What is the condition of S and R? You write it step by step, then you will understand the flow. So, this capacitor is, this BJT is actually discharging. The moment it is, if it is off, this is disconnected, right. If this is on, this will be pulling this capacitor to 0. This is another connection, that is ANCKTEL. So, you think about these two connections, and if you have any problem you can contact me offline.